here battling the snow and all.
Yeah, it's pretty bad out there. We got like 8 inches over the course of like 1 hour last night.
Well, since I shoveled it, I'm well aware.
I,
Yeah.
my roommate was up all night, and I wake up at like 4 o'clock in the morning, because I just need to grab some water. She's out there, and she's just like, "Yeah, it snowed like a foot in like an hour and a half."
I just want it to be clear for like 2 days in a row. It's,
It's 2 days in a row. The anyway, any questions or problems? Anything? Again, technically, that first homework was due yesterday at midnight, but again, the OWL does not ever close until the end of the semester, so you can still do it whenever you find the time. We were talking about these heating and cooling curves, so now we're more specifically talking about actual energy as measured in joules, right? We had been measuring intermolecular forces sort of indirectly as a temperature issue. In this case, since I'm now talking about actual joules, this is a real energy measurement of the involved energies. And if I'm going to conduct phase changes, in this case at constant pressure, because I'm only looking at the temperature piece of it, right? I have to consider the phase change to be a combination of really two different types of energies, right? There's my temperature / kinetic energy, and then there's, if you will, the energy associated with actually breaking the intermolecular forces, which is that phase change energy. And so again, there's no way to start at the beginning and go straight to the end, right? Because each step along the way is uniquely different, especially depending on what the specific material is, right? This is water. If it was always water, you could probably come up with an equation that would do it, right? But if I freeze or melt or boil a different substance that has different specific heats, that has different delta H's, and so, either you'd need a different fancy equation for every single substance, right? Or you'd need a really complicated formula that involved all the differences. So the easiest way to do it is essentially to construct your own complicated algebraic formula by looking at each step as a different process, right? And so really you can go either way here, by which I mean you can go, sort of left to right or right to left. I have the ability to add energy, or I have the ability to take it away, right? And so, if I start here and I go this way, I go up, across, up, across, up. If I start here and go down, I'm just doing the reverse, right? And each line is a little different because the physical constants are different. So my slope lines are sort of the classic MC delta T's that we had in Chem 1. We talked a little bit about delta H's in Chem 1, right? My flat parts of that journey are really just delta H's. Those are delta H's of phase change as opposed to delta H's of chemical reactions, which is the more typical delta H we would have seen in the fall, right? But up in the right-hand corner there's the numbers for water. Different phrases have different specific heats, right? And different phase changes have different delta H's associated with them. And so it's really just a question of the identity of the substance and the amount, right? The specific heats and the delta H's are associated with the material, right? All of those values are relative to amount. My specific heats are relative to mass, typically, although there are molar specific heats you might recall, which are sometimes abbreviated with an S instead of a C, which are typically joules per mole as opposed to joules per gram. So as always, let the units be your guide. In this case, they're mass specific heats instead of mole specific heats. So I need to know how many grams I have, right? The delta H's are far more typically in kilojoules per mole. Of course, if you wanted, you could express them in kilojoules per gram. It's just a molar mass away. And so again, you know, always be cognizant of the units for constants because you will find different versions of them, of course, because different versions exist depending on the application. All right, in this particular case, these are the more common sort of chemical units for the two different types of constants, right? And so it's MC delta T where M is mass, it's N delta H where N is moles, and my total amount of heat involved is unsurprisingly the sum of all the different energies along the way, because, and this is essentially where we left off on Wednesday, because of course energy is conserved, and so there's nothing disappearing or going away. There's no, you know, discount for doing the second process if you've already done the first process or whatever. And so, right, if I've got a problem where I'm heating or cooling it, I have to first and foremost be cognizant of what the phase change temperatures are, right? Because it's going to make a difference to the total energy of the trip, right? In the fall, when we were doing this, we didn't change phases, right? So every time I was adding heat, it was just an MC delta T and the temperature changed, right? But as we've seen, that works fine as long as the phase doesn't change. When I get to a phase change, there's an energy involved, all right? Breaking the chains, as I sometimes call it, right? But there's no temperature change involved. And so I have to break up my journey into steps. And as I sort of alluded to on Wednesday, these problems are deceptively simple as phrased. And again, if you want to be a student instead of a thinking scientist, right, you will do the natural thing, which is try to somehow take my three numbers and multiply them, add them or something and get an answer. In fact, I cannot go directly from 100 Kelvin to 500 Kelvin. And it's not a single process that gets me there because of the phase changes.
I have a quick question.
Yeah.
So let's say you have a pot full of ice and you're about to boil it. So as you start to boil the ice, all the energy theoretically would be going into the ice melting, not, you know, heating the water that's already melted. But, you know, in like realistically, wouldn't some of the water in the pot start to change temperature as some of the ice is still continuing to melt? So wouldn't like two of those things kind of happen at the same time?
The question on for those of you in the room, was if I threw water on a stove, ice, right? Do I not have water heating up at the same time ice is melting? And the answer is yes, to the extent that you really have multiple samples at some point, right? Once the ice starts melting, you've got both solid ice and liquid ice. There is nothing in this process that is time related, right? That is the overall process. You could be doing all five of those things simultaneously. That doesn't change the fact that the total amount of energy involved in doing the whole journey is the same. It does not matter if they're happening simultaneously or separately.
Thank you.
Yep, does that make sense? So, again, the phrasing of the question is relatively straightforward. I've got a starting point, I've got an ending point. Frankly, now again, because this is still water, it might be obvious to you, right, that there are 5 steps in this process. There don't need to be. right? Really, the first thing I need to do is orient my journey relative to what the phases are. So, you know, if I change this slightly, I have 50 grams of X at 100 Kelvin, right? How much energy to get to 500 Kelvin? The first thing I really need to do is figure out what the melting point and boiling point of X are, right? In fact, I don't even know what phase X is in if I don't know what the melting point or boiling point is, right? At 100 Kelvin, X could be a solid, liquid, or gas. I don't know what the melting point or boiling point is, right? If the melting point of X, right, happens to be 1800 Kelvin, which immediately suggests to you what? X is what kind of substance? Anybody? It's probably ionic, right? Either that or it's some really big molecule, right? Because it has a very high melting point. Well, there's only one thing going on here. X is heating up. There's no phase change. And X is a solid the whole time. On the other hand, if the melting point of X is 50 and the boiling point is 150, right? Well, now I've got two things going on. I start at 100, which is between 50 and 150. So I start as a liquid, right? And so I'm going to heat up. I'm going to boil at 150, right? And then I'm a gas the rest of the way. So where my starting and ending points are really depends on what the phase change temperatures are. And so the sort of generic journey is at most a 5-step process. But again, right, this is generically the melting point. This is generically the boiling point. I really orient my journey relative to those. If I happen to be starting here, I'm starting as a liquid, right? If I happen to be starting here, I'm starting as a solid. If I'm starting here, I'm a gas the whole time, right? And so my starting and ending points really determine, right, how many steps there are in the process, right? And so really my first thing is not to immediately grab my calculator and start punching numbers into it, even though that is sometimes the assumption in chemistry or life, right? I really need to consider what the actual process is I'm looking at. In this case, it's water. And so my orienting is relative to the normal boiling point and the normal melting point. And so if I'm starting at 100 Kelvin, I'm down here. And if I'm ending at 500 Kelvin, I'm up here. So I have to do all 5 of these things. All right. But that's okay. As I sometimes say, it's not harder, it's just longer. Instead of one little algebraic equation, I have 2, 3, 4, or 5 algebraic equations. But again, as long as I'm thinking my way through the process and only trying to do one thing at a time, not that hard, right? If I'm staying in the same phase, I'm just changing temperature. That's an MC delta T. If I'm changing phase, my temperature stays constant and I'm a delta Hing, right? And so again, these numbers in the book, on the internet, please be cognizant of the units, even though I couldn't quite squeeze them all in. All right. Also, please be cognizant, if you're going to add them all together at the end, they all have to be the same unit. Meaning, quite typically, the delta H's are in kilojoules, and quite typically, the specific heats are in joules. And so I need them either to all be joules or all be kilojoules if I'm going to add them together. In this case, I made them all joules, which is why this became this. Doesn't quite fit, but I can squeeze it in. Right. And so it's mass times specific heat times change in temperature, or it's moles times delta H. Right. Either way, my entire journey is just the sum of whatever steps I have to take. Right. It's worth noting, you know, there's sometimes some confusion over the signs, right? Because typically the delta H of vaporization is written for vaporization, but I could be moving the opposite direction, in which case I need to change the sign. Technically, the delta T's have a sign associated with them. It's always final temperature minus initial temperature, right? But if you're not being careful, you can end up with one of them looking like it's negative and one of them looking like it's positive. And I just say, for your edification, right, they should all end up with the same sign. You never have a case where you increase the temperature and there's somehow a negative delta H associated with the phase change, or vice versa, right? You're never decreasing the temperature, right, and suddenly have a positive delta H associated with the phase change. And so they're either all going to be positive or all going to be negative, right? It's the same quantity of heat no matter which direction I'm going, but negative technically means you're removing the heat, and positive technically means you're adding the heat. And again, if I crunch the numbers, right, again, as I mentioned the other day, the biggest number almost always is the energy associated with boiling. That is the hardest thing to do, right? It is the most dramatic of the phase changes because now my molecules are completely free. Right. Yes, no, maybe. Okay. And again, from a phase diagram standpoint, right, I'm traveling along a horizontal line when I do that because I am not in any way considering the effect the pressure might have. I am not in any way changing the pressure. Right. I can make phase changes with pressure by holding the temperature constant. And the reason goes back to what we were talking about also on Wednesday, right? Boiling, which is my liquid vapor phase change, vaporization, right, is specifically defined as the vapor pressure being equal to the atmospheric pressure, right? And so if I'm doing this, right, what I'm really doing when I increase this temperature to get to the boiling point is increase the vapor pressure. Because my atmospheric pressure hasn't changed. And so the whole reason it works to increase the temperature to get to boiling is because the vapor pressure increases as the temperature increases, right? We talked about that a little bit on Wednesday. My whole temperature curve moves over, right? Meaning there's more molecules that are energetic enough to enter the gas phase, right? So I could do the opposite, right? If I don't change the temperature, then the vapor pressure is constant. All right. But that's okay. All I need to do is to get the atmospheric pressure equal to that. All right. And so I could get something to boil by changing the pressure in the container, right? And so I can determine the pressure I need if I know what the vapor pressure dependence is with temperature. And then I can sort of do both. The Clausius-Clapeyron equation is the temperature dependence of vapor pressure. Right? As it was originally constructed, it looks like this. Right. In recent years, I've become obsessed with thinking of these equations not as some God-given truth handed to man on stone tablets in the lab, because they're not. Right? Almost all of these relationships, from the ideal gas law, right, to MC delta T, to the Clausius-Clapeyron equation, were determined experimentally. And so, like most experiments, and this is worth noting because it's far more generic than this one equation, there is always some knob that I can turn, some independent variable, as they are termed, right? And then there is some dependent variable that responds to it. In this case, the vapor pressure, right? In terms of actually doing science, right? Really the hard part, I shouldn't even call it the hard part, but the part that requires the most thought is being able to isolate a single dependent variable, right? And so my experimental design is frequently designed around eliminating competing processes, because it becomes much harder to figure out what's going on if 7 different things are happening at the same time. Since it was asked earlier to go back to, you know, my chunk of ice in a pan on the stove, right? It makes it hard to understand the individual steps in that process if I do them all at once. I can still get a number, right? It took me 10,000 joules to boil away my chunk of ice, but I don't know where those joules went. And so if I'm doing that experiment, I want to heat it very slowly, right? So it all melts before it boils, right? And so my experimental design here has to be done so that the only thing that's being allowed to change is the vapor pressure, right? If I do that, what Clausius and or Clapeyron, and frankly, probably really just their graduate students, really did was to just measure the vapor pressure at a whole bunch of temperatures and make a graph. Right, that's why this equation has this form. Right, it's really a y equals mx plus b, right? And normal graphing theory says the y value should be the dependent variable. The x-axis should be the independent variable. And I end up with a slope, which is actually a combination of 2 constants, and I end up with an intercept, which is now another constant. I don't say this to disillusion you, but it's worth saying, right? In a lot of cases, that's where these quote unquote constants come from. They are, again, not some divine truth handed down to man on a stone tablet. They might not even be real. I mean, this one's well studied enough and well established enough that it's probably real, right? But if you're Clausius and Clapeyron and you do this, right, you come up with a slope, right, which looks like it's some kind of physical constant for water, right, or ethanol, or whatever liquid you picked. And you come up with a C value, which looks like it's some kind of physical constant, because every time you do water, you get the same C value. It doesn't have to be anything real or theoretical. I mean, again, this is, 140-year-old or 130-year-old equation that's been well studied. And so there is theoretical support for the assignment of the slope and the intercept. But if you were really doing something new for the first time, you get a slope and an intercept. It might even be constant. You can call it, the Joe constant. But I don't necessarily know it to be anything real. It could be an artifact of the experiment. In fact, a colleague of mine in graduate school is either very lucky or very unlikely or unlucky. I'll tell you the story, you can decide. So he was there in his 4th year. He's writing up his thesis. He gets it all put together. He defends, he graduates. 2 months after he graduates, they discovered that his discovery was an impurity in his protein. It was sloppy science, but he got a nice result, and he had these graphs, and he had this data that suggested this number was a thing, and it wasn't. So, the bad news is he spent 4 years doing experiments with dirty protein. The good news is he graduated before anybody figured it out. So, he's either the luckiest or unluckiest colleague I ever had, or maybe both at the same time, right? But the same issue, if you're Clausius and Clapeyron, you get these constants, you don't know necessarily what they mean in terms of underlying molecular motions or anything else until later. And so I have essentially 3 constants, right? R is the gas constant. That's kind of a universal constant these days. And then I have what are 2 material specific constants, right? This is my delta H of vaporization. This is what's known as the Clausius factor. These are material dependent. So water has a different value than ethanol, which has a different value than gasoline. All right. And this equation in this form is perfectly reasonable. It's perfectly useful, and it's really a great idea if you're making a graph. Right? Because it's already in y equals mx plus b form. Right? It's also, perfectly usable as an algebraic expression. If I happen to know delta H, R, and C for my specific substance, plug in any temperature and I get the vapor pressure. All right. Delta H of vaporization, usually known because you can usually get it if you do this. All right. The Clausius factor is less well known for materials. All right. And so while this is a usable algebraic expression, if I can go to the internet and find delta H and C for my specific substance, it is sometimes hard to find the Clausius factor. Right. And so there is another equivalent representation that is sometimes more useful because it doesn't require me to know C, right? I almost always know delta H. I don't always know C, right? And this is kind of a neat algebraic trick that we'll use again later. And it works for a lot of things because all I'm really doing now is comparing 2 data points, right? If you think about it, plotting a line is generally speaking comparing multiple data points. I mean, you can do it with 2 data points, but that's sort of cheating, right? I mean, you'll always get a straight line with 2 data points, right? So you usually draw a line when you have 3, 4, 5, or 10 data points. It's a way of simultaneously comparing all the data, right? On the other hand, if I've already established that it's a linear dependence, then I could just look at 2 data points, right? And so my 2 data points are 2 different vapor pressures at 2 different temperatures, right? And I just want to compare them, right? And, as a general rule, because I'm all about process over results, compare almost always means subtract or divide, right? I mean, if you think about it, multiplication and addition aren't making comparisons, they're making combinations. 10 donuts plus 2 donuts is now 12 donuts, right? If I divide or subtract, I'm actually comparing the relative size of the numbers. If I subtract them, I'm looking at the difference between the numbers. If I divide them, I'm looking at the ratio between the numbers, right? And so if I want to compare those two data points, I could either subtract them or divide them. In this case, subtracting them is more algebraically simple, although I could also divide them. And so I literally subtract equation 2 from equation 1, right? So I subtract both left-hand sides and I subtract both right-hand sides. Since the left-hand side should equal the right-hand side, I should still have an equality. Now I know what you're thinking. I hated that equation to begin with. It had a log in it. You just made it harder, right? Because I now have like 10 different variables, right? Except I don't really have 10 different variables because a lot of these are the same and even more useful, right? The Clausius factors cancel, right? I've got here a C minus a C. All right. And so I've actually removed what I have claimed without proof to be the troubling constant in there that I have trouble finding. And so I get a simpler equation. Now I know what you're thinking. That's not simpler, buddy. I maintain it is, right? Because it's not a question of how many letters I have in the equation. It's a question of how many of them I know, right? And so in this case, I have kind of added a couple variables, but I potentially added variables I know at the expense of the Clausius factor that I didn't know. Right? And so I sometimes refer to this is just my terminology. You probably won't find it on the internet, well, until you go to Course Hero and find my answer keys. Whoops, Clapeyron. This is the 2-point Clausius-Clapeyron equation, as I call it, because it's really the comparison of two data points in Clausius-Clapeyron. But it's really useful, especially for common substances, because even though, right, there are technically all those different variables, I actually know all but 2 of them. Right? Because one of the things I almost always know for a common liquid is the normal boiling point. Right? I'm even more likely to know that than the delta H. Right? And by definition, the normal boiling point, right, is the temperature at which the vapor pressure is trying to keep you alive, right? So I technically know the temperature at which the vapor pressure is 1. That's what I call the normal boiling point. So I kind of replaced my Clausius factor, which is hard to find, with the normal boiling point, which is easy to find. Probably the easiest thing to find. R is the gas constant. I always know that. So all I need is delta H of vaporization. And so there's 2 ways I can use this, right? I could determine the vapor pressure of water at a different temperature. Right? For example, I might want to know what the vapor pressure of water is at 50 degrees C. Why would I want to know that? Well, it's really a question of how moist the air is. This is essentially a relative humidity issue. Right, relative humidity is essentially how much moisture is in the air relative to what the vapor pressure of water is. Because if the amount of water and air is equal to the vapor pressure, it's sort of the reverse process. It starts condensing. Right. And so I might care what the vapor pressure of water is at 50 degrees C because I'm going to do my reaction at 50 degrees C, right? And I want to know how much water is in the air, especially if water is getting in my way for the reaction. And so it is a Clausius-Clapeyron problem because that's what Clausius-Clapeyron tells me. What's the vapor pressure at any particular temperature? If I know delta H and C, I could use the line version of Clausius-Clapeyron. On the other hand, again, for common substances, because I normally know the normal boiling point, quite frequently this 2-point Clausius-Clapeyron is easier to use, right? Because I know the vapor pressure, right, at the normal boiling point is 1 atmosphere. So that's 2 things I know, right? I'm trying to determine the vapor pressure at a different temperature. So that's the one thing I don't know, and the temperature at which I don't know it. R is R. And again, delta H I can look up. And so at that point, it essentially is a plug and chug. Right? It's worth pointing out a couple things about the units, and the numbers. Right. My units have to cancel. Right. And so, right, what I've got here are units of reciprocal temperature. Right. So this is a Kelvin, well, really a 1 over Kelvin or a 1 over degree C or a 1 over degree F. More on that in a second. Right. Over here, I'm unitless. Right. I've got a vapor pressure over a vapor pressure. The units cancel. So on the right-hand side, all the units also have to cancel. All right. And so here's where my constants become an issue, right? My delta H of vaporization, if I look it up, almost always kilojoules per mole. All right. The normal value of R we were using for the ideal gas law back in Chem 1 was, you might recall this number. It doesn't have terribly helpful units. It's exactly equivalent to the number I have written there, which is the other most commonly encountered number for R. You can find R with all kinds of fancy units. Like, you'll love this one, Pascal's meters cubed per mole Kelvin. Right? In fact, Pascal meters cubed are the SI units for pressure and volume. You'd almost argue that's the preferred unit, even though you never see it, right? Because again, it becomes an issue of what units you're trying to cancel, right? In this case, since I've got kilojoules per mole up here, and I need to end up unitless, down here, I need to have kilojoules per mole Kelvin. All right, and so this is really a general rule. Well, rule might overstate it, but it's a general issue. If you've got energy, that's usually the R you want, because that's R in terms of joules, and joules is our energy unit. And so you tend to see both of those R's quoted if you go to a table of constants. And it's really just application based. If you're doing an ideal gas type experiment where pressures and volumes matter, the liter atmospheres make sense. If you're dealing with energies, right, you need the joules. Right. The other thing that's also a very general rule is if energy is involved, I need kelvins. Because it's a question of the zero, right? The only thing that really sets kelvins aside from my other temperature units is Kelvin has an absolute zero, right? 0 kelvins is 0 motion. 0 kelvins is 0 energy. Right? And so if I'm going to get the right limiting behavior, I need to have the 0 in the right place. So if I'm talking about energy, it is also always kelvins. All right. Yes, no. The third thing worth noting, I saved the best for last, right, is if you look up almost any substance, they will usually quote 2 different delta H's of vaporization. They will quote the delta H at the boiling point, which in this case is 100 degrees C or 373 kelvins. And they also will almost always quote the delta H of vaporization at standard temperature, which is 25 degrees C. Right. In some sense, that's the difference between evaporation and boiling. Right. But they almost always quote both. Right. In the context of Clausius-Clapeyron, right, the standard temperature delta H is most frequently used. It is worth pointing out, in an attempt to disillusion you, right, that this actually points out the fact that Clausius-Clapeyron is not, in fact, an absolute truth handed down from God to man on stone tablets. Because Clausius-Clapeyron is at least a little bit wrong. Right, in the sense that Clausius-Clapeyron essentially assumes that the delta H of vaporization is temperature independent. Right, that might be clearer, right, if I go back to the original formulation of Clausius-Clapeyron. Right, this only works if this delta H and this C are good at this temperature. And so if I'm going to use this at multiple temperatures, I either have a useless equation where every time I change the temperature, everything changes, or those constants are temperature independent. In fact, as we just proved for water, delta H is not constant. Slight flaw in Clausius-Clapeyron. And so it's not perfect. All right. But at this point, again, since standard temperature is the delta H that gets used, I now have a value for everything except the vapor pressure at 50 degrees C, which is 323 kelvins. And so at this point, it's essentially a plug and chug. All right, again, be a little careful with the algebra here because I have seen any number of mistakes here. In theory, you should be able to more or less punch a lot of this into your calculator all at once if you use the brackets properly and get the order of evaporations right. If not, please, please, please do it in multiple steps. The first thing that frequently gets done is 1 over 373 minus 1 over 323 is not 1 over 50. All right, you're subtracting fractions, they need to have a common denominator. So I just did them as decimals there. I need the units to cancel. And so I either need my kilojoules in the delta H to be joules to match the R, Or I could have changed the joules and the R to kilojoules to match the delta H. But whether they're joules or kilojoules, they have to be the same or they won't cancel. Technically, the vapor pressure could be in any unit of pressure you want. Since I had 1 atmosphere here, there's no reason for me to change that. I don't have any reason to prefer inches of mercury or pascals or something. All right, and so I've got nothing but a bunch of numbers on the right-hand side. If I crunch them all into my calculator, I get that magnificent number, 2.194444, 6789. Probably way more digits than I need, but I also have no reason particularly to round it here. At least not yet, right? And then I have that good old natural log term, which everyone hates. But that's okay. At this point, it's easy to get rid of. I just need the anti-log, which is e to the x. So I essentially raise e to both sides because e to the log essentially cancel each other, and e to the 2.19 is just a number, right? And then I can solve for the vapor pressure. And I get 0.111373. Again, at this point, rounding probably makes sense. I really don't need more than 2 or 3 sig figs probably. All right. I asked the question because you always should. Does this make sense? All right. That's a hard question to answer, especially if you're a novice in any field, right? But the context in which I ask it and answer it here is really relative to my 1 atmosphere, right? 50 degrees C is below the boiling point, right? The vapor pressure must therefore be below 1 atmosphere, and it is. Right. You can also view this result in reverse, right? That tells me the vapor pressure of water at 50 degrees C is 0.111. That tells me how much water's in the air. It also tells me how to boil water at 50 degrees C. If I reduce the atmospheric pressure to 0.111 atmospheres, my water boils at 50 degrees C, because then my atmospheric pressure equals the vapor pressure. All right. And so really the other way, I will leave you with this, but it's here. The other way you can use Clausius-Clapeyron is to do just that, which is determine what the boiling point is at reduced pressure, or how to boil something at a temperature less than the boiling point. All right. And maybe we'll pick up with that on Friday. Where does the week go? Questions or problems? Be careful on the ice. We don't need any broken bones. Happy hump day. I will see you Friday. I am here if you have questions.
Professor Lanzafame, I was
Yeah.
just wondering, are all the Sen gauges just due every Tuesday from now on?
They are technically due every Tuesday, yes.
Okay, thank you.
Yep. Except we have one Tuesday recovery day, in which case they're not due till Wednesday.
Oh, all right.
Since
Thank you,
nothing is,
Professor.
yep, have a good day. Nothing's due on recovery days. And Dwight?
Professor, I was having an issue with the WebAssign. One of the questions, it asked about, it was on the first one, it was asking about what type of like atomic structure was there, but there wasn't any example. It was just like an option for,
It might be Flash. I don't know what browser you're using.
I
mean,
Chrome.
Well, I mean, I don't know if it's Flash animation. You need to have Flash enabled. Again, I don't really
Okay.
know. I don't really know what you're seeing or not. But
I'm trying to.
That's one
pull it up.
possibility.
Okay, I'll see if it's a browser thing. Thank you.
It should be. Is that the what do you call it? Intro to Cengage thing, or